Hello. In this lecture, we are going to review some fundamental circuit elements, and we are going to revisit Ohm's law, and we are going to wrap up this lecture with Kirchhoff's law, namely KCL and KVL. KCL stands for Kirchhoff's current law, and KVL stands for Kirchhoff's voltage law. One deals with voltage, while the other one deals with current. These two laws are very important that you're going to see them very often throughout the course. So now I'm going to move on to the first part of the lecture. So electrical current. So an electrical current is defined as the rate of positive charge flow. And this electrical current is denoted by I, and the unit associated with this current is ampere, and we usually use A for that. This electrical current has polarity, and I'm going to say quote unquote here, and this polarity generally is referring to the direction of the current flow rather than the positive and the negative sign. When we talk about voltage, you will see that the polarity has to be specified with positive and negative. But for current, it is important that you always specify the direction, whether the current is flowing to the right or to the left, to the top or to the bottom. So I is equal to dq over dt, change in the charge with respect to change in time. This Q is your charge in coulomb, and T is the time in seconds. So by taking the derivative dq over dt, you can find your current, okay? So this is yet another important equation that you will see again and again when we talk about capacitor and other time domain circuit analysis. Current density. Current density is defined as the rate of positive charge flow per unit area. Now, notice that rate of positive charge flow is nothing but your current. So your electrical current per unit area. So you can expect that the unit is going to be some ampere divided by centimeter square, where this square is referring to your area. And of course, depending on the dimension of your, for example, a wire, conductor, you can have A per meter square. Okay, so in this case, I'm using centimeter square. So instead of using I, we're going to introduce this J. So J is used to denote current density. Current is denoted by I, and the current density is denoted by J. And the unit, again, is ampere per centimeter square. So as an example, if I have a wire with a cross-section area like this is the length of the wire. I have to specify the direction of the current flow. For example, in this case, I indicated the direction of the current by using this arrow, which tells me that this current is going from left to right. Now, at the same time, the electron is going to flow in the opposite direction. So if the current is going from the left to right, then the electron is going to go from right to left. Okay, so current and electron are always flowing in opposite direction. Right, and the reason, right? So if you look at the current, the definition of current is defined by this rate of positive charge flow. Positive charge. while the electron is negative charge. So one is positive and the other one is negative, so naturally they have to flow in the opposite direction. Next, let's talk about electrical potential, aka voltage. So an electrical potential or voltage is defined as energy per unit charge. And this is denoted by V, and the unit is volt. So this voltage, this electrical potential, mathematically is equal to dW over dQ, where W is energy or work done. And the unit associated with energy is called joule. And Q is the charge in Coulomb. Okay. So by taking this derivative, you can find your voltage or electrical potential. Now, notice that when we talk about current, right, I mentioned that there is a quote-unquote polarity that you have to specify, right? And that indicates the direction of current flow. Now, similarly for voltage, we have to specify the polarity, okay? And this polarity is denoted by plus and minus. Plus tells you the higher potential. The minus tells you the lower potential. So in this case, I have VAB here, right? So this is point A and this is point B. This is the voltage at point A and this is the voltage at point B. Now, if I want to calculate the potential difference across this element, right? Whatever this element is, right? It can be a simple resistor. The electrical potential across this element is simply denoted by VAB, and this is defined by VA minus VB. And this tells me that the voltage at A has higher potential compared to that at B. Okay. So I have plus here and minus there. Okay. So this tells me that I have some potential difference, right? In order to create a difference, you need to have some delta. And that delta comes from the difference between this plus and the minus. Okay, so it is important, right? So to keep in mind that potential comes, this potential difference comes from some delta between two node voltages. In this case, I have VA minus VB. Next, I have electric power. Okay, so electric power is defined as the transfer of energy per unit time. And this is denoted by P, and the unit associated with this energy is, the unit associated with this power is watt. Okay? So P simply is equal to dW over dt. Okay? Derivative of this work done, this energy, with respect to time. Okay? And this simply is equal to dW over dQ, right? I can decompose this term into something that we just learned. dW over dQ, which is simply this voltage, and dQ over dt, which is nothing but your current. Okay. So by doing this, I know that P simply is equal to V times I, or I times V. They're the same. So as a positive charge Q moves through a drop in voltage V, you will lose energy. Delta W, change in energy, is simply equal to the charge times the voltage. Okay. So let me give you some more example here. So I wanted to specify the polarity associated with the current flowing through this piece of wire. So assuming that I have a current of 4 amps going from left to right, From left to right, I have 4n. So therefore, the current going from the right to left is going to be the opposite of whatever this number is. So if going from left to right is 4n, then going from right to left is going to be minus 4n. There's a negative sign, okay, which tells you that these two currents are indeed flowing in opposite direction. Okay. So keep in mind, it's very important for you to specify the direction of the current flow, right? You never want to just write down your current I equal to 4n without specifying the direction, because people will not know, right, in which direction the current is flowing. In the context of voltage, so suppose I have some element here, right? Simple resistor as an example. So if the voltage drop across these two terminals is equal to 5 volts, then I can reverse the polarity associated with these two terminals. If I put a negative here and a positive here, then all I have to do is I change this voltage from plus to minus. I change the sign of this voltage. Whatever this voltage is, I just need to attach a negative sign. Okay? So in this case, I have 5 volts here, plus here and minus there. And in this case, if I reverse the polarity, I have minus 5. Okay, and these two are the same, obviously, right? Okay. All right, so again, it is very important in order for you to do your circuit analysis correctly, you have to specify the reference direction for the current and the polarity for your voltage. Okay. All right, so another simple example here. So I give it away. So suppose you have an unlabeled battery and you measure its voltage with a digital voltmeter, right? Something that you use in the lab to measure the voltage. It'll tell you the magnitude and the sign of the voltage like this, right? So as an example, I have some battery and I have this DBM hooked up this way. So the positive terminal of this DBM is going to this terminal of the battery, and this ground is connected to the other side of the battery. Okay, and then the question is, what is VAB, right? So notice that I'm asking for a specific voltage in a specific polarity, right? VAB, meaning this is my node A and this is my node B, right? I want to know what is the voltage like this. This is my VAB, okay? So what do you think VAB is? Well, based on this reading on the DBM, I'm seeing minus 1.5 volts. When I ask what is VAB, I expect the voltage to be specified this way, plus associated with A, minus associated with B, right? Because from earlier, we know that VAB is equal to VA minus VB, whatever the voltage at node A minus the voltage at node B. That's what VAB means. But based on this reading on the DBM, I see minus 1.5 volts. Okay, I see minus 1.5 volts. So what does that tell me? Right? It tells me that this VAB is simply equal to minus 1.5 volts. Right? I'm just reading it off straight from the DBM. So what this also tells us is that VA, the voltage associated with this terminal, okay, is lower than VB over here by how much? By 1.5 volts, right? Because I have a negative sign here, right? This is a negative voltage. So I know A is going to be lower than B. In other words, B is going to be higher than A. Okay, so this is simple enough for you to figure out mathematically, right? And of course, if going from high to low, plus to minus, I have minus 1.5, right? Then you know that VAB is equal to minus 1.5, or you can say VBA is equal to plus 1.5 volts, right? All I did here was I changed the subscript and I reversed the sign. I changed the subscript. Instead of AB, I changed it to BA. Instead of minus, I changed it to plus. Minus 1.5 volts, which gives me plus 1.5 volts, right? So again, this shows you that VB is higher than VA by 1.5 volts. Okay, so of course, which side is the positive terminal of the battery, right? So now you know that the one with the higher potential, VB, is going to be the positive terminal of your battery. Okay. All right. So now throughout the course, you're going to see some ground symbols used in the notes and also in your textbook, right? And depending on the context, well, depending on the book, okay, or the reference notes that you read, sometimes people use this symbol, and sometimes this symbol is used. Okay, so in this case, right, you see these two symbols sometimes used interchangeably in this lecture notes, and I try to keep as consistent as possible, right? So in this case, I'm not trying to make a distinction between these two symbols. Okay, so you'll see that sometimes I use this and sometimes I use this, but most of the time I probably use this. Okay, so this is just something that I wanted to mention so that when you read the notes, you don't get confused. They basically mean the same thing in this lecture notes. Okay, so the next topic I wanted to talk about is the sign convention for power. Okay, so for power, we know that P is equal to V times I, right, or I times V. Okay, so current times voltage, voltage times current. So if I have some element, right, passive element, right, so let's say I have a resistor here. If I have a resistor and I apply some voltage across this resistor, I expect to see some current flowing into this resistor. So if I want to calculate the power delivered to this resistor, then it's going to be simply just P is equal to V times I. Okay. What I can also do, right, is instead of applying plus here and minus there, I can apply plus on the bottom and minus on the top. Okay. So in this case, since I have changed the polarity of the voltage that I apply, then I expect the current is going to flow in the opposite direction. Okay, given that whatever inside this box remains the same, right? If this is a resistor here, then it has to be the same resistor over there, right? So that I can make a fair comparison here. Okay, so if I have plus minus V here, I have current flowing into this resistor. If I have minus and plus here, I have current flowing out of this resistor. Okay, so this is the power delivered to this resistor. Okay, and I'm going to use this as my passive sign convention. Okay, if this is indeed the case, if power P is greater than 0, right? P is equal to V times I. If this P is greater than 0, then I say that this power is delivered to this box, right? Let's say it's a resistor. Now, if I have this setup over here, so let's say I have another box, and inside this box is not a resistor anymore. Okay, inside this box is not a resistor anymore. I'm going to put a question mark here, right? If I apply this voltage plus here and minus there, okay, same voltage, right, but different element inside this box. Instead of seeing current I flowing from left to right, now I'm seeing the current returning or flowing from right to left. Instead of delivering current to this element, now I'm seeing this element deliver or return current back to me. I'm seeing this element returning current back to this voltage source, right? Because in the beginning, I apply some voltage source. In this case, I apply some voltage source. This current is going into this box, but now I apply the same voltage, but not a different box is returning some current back to me, back to this voltage source. Okay, so clearly, these two scenarios are not the same, right? Because on the top, I have P equal to V times I, but on the bottom, I'm going to have P equal to minus V times I. Why minus, right? So the minus sign comes from the fact that this is opposite from my passive sign convention. My current, instead of going from left to right, is now going from right to left. Okay, and similarly over here, if you compare the two cases, right, you're going to see that current is now flowing in opposite direction. So in such case, my P is less than 0, right? Because I have a negative sign here. So P is less than 0 over here and is greater than 0 over there on the top, right? So P is less than 0. So in that case, the power is extracted from this box. Instead of delivered to the box, now the power is extracted from the box. Okay. I'm going to invite you, okay, to think about what can be inside this box such that you can have this power that is less than 0. Right? This is a little counterintuitive, but such kind of circuit, okay, does exist. Okay, so I'm going to invite you to think about what could be inside this box. Okay, very interesting problem. Okay. Okay. So just to wrap up this part of the discussion, so power. So if an element is absorbing power in a case where P is greater than 0, then we know that positive charge is flowing from higher potential to lower potential, right? So that's pretty clear. So then the question is, how can a circuit element absorb power? So you're going to see this very frequently in your daily life, right? So for example, we can convert electrical energy into, number one, heat, right? In the context of toaster, right? So resistors inside your toaster. And we can convert electrical energy to light, right? So light bulbs, for example. Can also convert electrical energy to acoustic energy, for example, driving the speaker, right? Audio. And we can also have energy storage, right? Charging a battery, for example. Okay. Okay, so the next I wanted to discuss is circuit elements. Basic circuit elements that you need to know for this course. Okay, and I believe these elements are something that you have come across in your prerequisite courses. Okay, so the first two are your voltage sources, voltage source and current source, and this voltage source and current source are considered as active elements. By active element, okay, I mean these sources are going to generate electric energy, some kind of energy. By they're active, they can generate some kind of energy. But since we are talking about electronic circuit, right? So we use electric energy in the context. The next group here, 3, 4, and 5, I have resistor, inductor, and capacitor, RLC. These elements are considered as passive. Okay? They are passive elements, elements that cannot generate electric energy. Right? So one is active, right? And they have the ability to generate energy, electric energy, and the other type is passive, right? There's no way for them to generate electric energy, right? They're very different, active and passive, okay? And we're going to use all these elements throughout this course, okay? And in fact, let me just give you some quick example here, or some heads up, if you will. So when we talk about op-amp, we're going to be using voltage source, current source, resistor, okay, to basically model the behavior of an op-amp. Okay, so op-amp stands for operational amplifier. It's considered as a very versatile block, right, for you to construct circuits with different functions. Okay, and this is the so-called operational amplifier. And to study the behavior of this operational amplifier, we can simply use simple voltage source, current source, and some resistors to model the behavior of this block. Okay, and this is something that we will learn in a week or so. Okay. All right. So electrical source. So this is pretty straightforward. So an electrical source is a device that is capable of converting non-electric energy to electric energy and vice versa. And electrical sources can either deliver or absorb power, right? So as I mentioned, P greater than 0 or P less than 0. Okay, so for an ideal voltage source, so what does an ideal voltage source do for you? So an ideal voltage source is a circuit element that maintains a prescribed voltage. So I specify a voltage across the terminal, right? So I have my, let me just draw it over here. So this is my voltage source. I have 2 terminals, okay? So it's a circuit element that maintains a prescribed voltage. So for example, if I specify 10 volts across these 2 terminals, okay, then this voltage is going to stay there. It's going to be always set to 10 volts. Always going to be set to 10 volts, regardless of how much current is flowing in and out of this voltage source. Right? So this current that goes in and out of this voltage source can be either very small or very large. But regardless of how large or how small that current is going in and out of this voltage source, the voltage is always going to be pinned at 10 volts. Right? Notice that the key here is to, I want this guy to maintain a prescribed voltage, right? This is something that I specify, right? Something that I want. And I use 10 volts here as an example. You can use 100 volts, 5 volts, 6 volts, and so forth. This voltage source, okay, or this voltage in general, okay, can be either independent or dependent. So let me give you an example here. If I have an independent voltage source, right, this is just what I drew over here. This independent voltage source is set to, for example, 10 volts. And it's going to always remain at 10 volts. And when I say independent, right, that means this voltage source does not depend on any external stimulus or any external variable, okay, at all. Okay. So this voltage source or voltage can be either independent or dependent. If we have some dependent voltage source, then this voltage source can depend on either a voltage or a current somewhere else in the circuit. And further, this voltage and this current can be either a constant or some time varying, okay, time varying voltage or current. So as an example, over here, I have a dependent voltage source. And typically for a dependent voltage source, it is denoted by the diamond shape. So it's not difficult to tell whether you have a dependent or independent voltage source. For an independent voltage source, it always has this circular shape, circle, right? For dependent voltage source, this type of voltage source is always drawn with a diamond shape, represented by a diamond shape. But of course, what's in common is that you see, you always have this polarity that you have to specify, plus here and minus there, plus here and minus there, right? You always need that, right? But the shape is different depending on whether you have independent or dependent voltage source. Okay, so as an example, I have Vs. This Vs is equal to some alpha times Vx. This alpha here is, you can think of this alpha as some scaling factor. So later on when we do circuit analysis, this alpha is going to be some numerical number. For example, 0.5, 2, 3, 10, whatever. Okay, some scaling constant, alpha, which is used to denote this scaling. Multiplied by Vx. What is Vx? Right? So Vx is, so if you look at this statement here, voltage can be either independent or dependent, right? And if it's a dependent voltage source, it depends on voltage or current somewhere else in the circuit. So this Vx is another voltage that exists somewhere in the circuit, right? So I'm only showing this dependent voltage source, but of course, assuming that, you know, this dependent voltage source is connected to another circuit, right? And somewhere in this circuit, you will see this Vx, right? And this Vs depends on this Vx inside this circuit. So in such case, I have voltage controlled voltage source, VCVS. Notice that this is a voltage source, and it's always a voltage source since we have plus or minus, right, to denote the polarity, right? But this is voltage control because I know there is some dependency, right? And that dependency is this Vx. So in other words, Vs depends on Vx, which is somewhere in your circuit, multiplied by some scaling constant. There's some number. Now, what I can also have is this. Same diamond shape, representing dependent voltage source, but instead of voltage control, instead of having this Vs depend on voltage, I'm going to have this Vs depend on current. So instead of voltage control, I'm going to have current control. So current control voltage source. Okay, so in this case, Vs is equal to some beta, right? Instead of using alpha, I'm going to use beta to denote, again, the scaling constant, right? And that constant can be whatever number. Okay, multiplied by Ix. And assuming Ix is somewhere inside this circuit. Okay, so beta times Ix is equal to Vs, which gives me current control voltage source denoted by CCVS. Vs always means voltage source. Cc means current control. Okay, so the dual of an ideal voltage source is an ideal current source, right? So in this case, so my current source like this. So this is I, right? So I'm going to use, let's say, 10 amp. Right? You can use 100 or 5, doesn't matter. So I'm going to use 10 here. So an ideal current source is a circuit element that maintains, again, the prescribed, right? Something that you specify, right? Prescribed current, not voltage, right? Because we are talking about current source. So prescribed current through its terminal, regardless of the voltage across these terminals, right? So again, I have these two terminals, and regardless of what I have across these two terminals, what I have across these two terminals can be either very large or it can be very small. It can be positive, it can be negative, but it doesn't matter, right? I don't really care about what that voltage is. All I care about is I need to have I need to maintain the prescribed current, okay, through this terminal, Okay, so if this is 10 amp, okay, then it has to stay throughout the course, right? Okay, so similarly, the current can be either independent or dependent. And the dependency can be on voltage, okay, or current elsewhere in the circuit. And again, it can be some constant voltage, constant current, or it can be time varying voltage or time varying current, right? So constant, right? Some of you probably know that constant refers to DC voltage, DC current, while time varying refers to AC, right? So these two will be discussed in the subsequent lectures. So as an example, this is my independent current source. So again, this is denoted by or represented by a circular shape, right? Just like your voltage source, but now without specifying the plus and the minus, I need to denote the direction of the current flow, right? Just like what we discussed earlier. Right? So you need to specify the direction of the current with this arrow. Now, if I have a dependent current source, right, so in this case, IS is equal to some alpha scaling factor times Vx, where Vx, again, is another voltage that exists somewhere in your circuit. Okay. So in that case, I have some current source that depends on some voltage elsewhere in the circuit. So in this case, I have something called voltage controlled current source, aka VCCS. Now, similarly, instead of having this dependency on the voltage, I can have dependency on current. So in this case, I have current controlled current source, right, by exactly the same rationale, right? So I can have this current IX exist somewhere in the circuit, and I can have this beta as my scaling factor. So IS depends on this IX somewhere else, and I have something called CCCS. CS means current source. Okay, so again, it is important for you to keep in mind that whenever you see a circular shape, you have independent source. Okay, you see a diamond shape, that means you have dependent source. And this dependent source can depend on voltage or current. Okay, circular shape applies for or is applicable to current source and voltage source. Okay, both. Likewise, diamond shape is the same, okay, for current source and voltage source. Okay, so let's move on and talk about electrical resistance. Okay, so this is probably one topic that you guys have seen in your physics course last time. Okay, and I think it makes sense for us to revisit this topic because we will be dealing with voltage, current, and resistor a lot in this course. Okay, so it makes sense for us to to understand fundamentally what resistance, what this electrical resistance is doing. Okay, so by definition, electrical resistance is simply the ratio of voltage drop current. The ratio, right? So I'm taking some ratio, right? So this ratio tells me that I need to take something divided by something, right? And by definition, right, I have to take the voltage drop divided by some current, okay? And this is my electrical resistance. So if I know the relationship, right, if I have voltage and current and I take the division V over I, then I can model the behavior of this circuit element, and that circuit element is called a resistor. Right? Now, without diving in further, right, by just looking at this equation, right, you can immediately tell that for a given voltage, the voltage is fixed. If I increase the current, then the resistance is going to be lower. So if V is fixed and current goes up, then R is going to be smaller. Okay. If V is fixed and I is smaller, then this resistor is going to go up, right? And keep that in mind. We're going to come back to revisit the concept in a second. Okay. The unit associated with resistor is ohm. So that is the reason why this is called Ohm's law. Right? So again, V divided by I is equal to R. So therefore, V is equal to I times R. So voltage drop, this V, voltage drop, is simply equal to I times R, the product of current and the resistor. Okay, so this is basically the equation that we use to represent Ohm's law. Okay. In this course, what you will be asked to do, right, when it comes to circuit analysis, is that you need to find at least one of these variables. Okay. So, for example, if I ask you to find voltage given I and R, right, then you need to know how to apply this Ohm's law, right, so that you can find your voltage. Now, similarly, if I give you V and R, then you need to know this Ohm's law so that you can find the current through the resistor, right? So it's always, one out of these three variables that you need to find in your circuit analysis. And of course, sometimes it's a little bit more involved, right? There's simultaneous equations that you need to solve, so you need to find multiple voltages and multiple currents and so forth. Right? Okay, so again, so this Ohm's law tells you the current flowing in the resistor is proportional to the voltage across the resistor, right? So this is a very simple circuit set up to illustrate that point. Okay, so I apply some voltage across the resistor. I look at how much current is flowing into this resistor. I measure this voltage, right? Or I know this voltage because I know how much I put in. I measure this current. I take the ratio V over I can find the resistor. Okay. So again, I apply some voltage. So let's say I have this voltage source. So plus minus, right, which is the same as this plus minus. So let's say this is numerically is 10 volts, right, 10 V. And I apply this, and I look at how much current is going into this R, right? So let's say this this current is, I'll try to measure it, right? I see 2 amp. Then in this case, I know the resistance is going to be 10 over 2, so I get 5 ohm. So I put in this, I measure this, I calculate this. Okay, so that means you know 2 variables and you find the third one. Okay. Now, instead of using electrical resistance, right? Sometimes it's more convenient to look at electrical conductance. Okay, so that is the reason why I wanted to revisit or review this important concept. Okay, so electrical resistance is important. Okay, but depending on the context, electrical conductance can be very useful. Okay, in terms of circuit analysis. So conductance is the inverse of resistance, right? Reciprocity, right? So we take the inverse, right? So conductance is denoted by G and has unit of Siemens or mho. So you see that this symbol is the opposite of ohm, right? So opposite of ohm is called mho, right? So some people also use Siemens. Okay. So as an example, if R is equal to 100 ohm, then what is G, right? So all I have to do here is I take the inverse of this resistance. So G is going to be 1 over 100. So this is going to give me 0.01 mho, right? Mho, okay, or Siemens. Okay, so I just need to take the inverse. Okay, so let's talk about these two important concepts, short and open. Okay, so what do you mean by short circuits and open circuits? Right. So in circuit analysis, okay, oftentimes you're going to make approximation, right? So approximation means you have to know how to compare, right? Relatively speaking, right? Let's say if you have two resistors, right, and you compare the size of those two resistors, and you wanted to see whether or not, right, you can simplify the circuit by, let's say, ignoring one of them, right, by making the approximation, relatively speaking, right, and you want to compare the order of magnitude between those two resistors, right, and before you do that comparison, perhaps it makes sense for you to understand the concept behind the so-called open and the short. Okay, so short circuit is denoted by just a simple wire. Okay, the wire that connects these 2 points together. These 2 points are electrically connected, and since they are electrically connected, this point and this point therefore have the same potential. Okay, same potential. Same potential means there is no voltage difference. There is no delta between this dot and this dot, because electrically this and this are the same. If they are the same, there exists no potential difference, no voltage difference. Okay. So in that case, the current, right? So for example, if I have current going this way, right? The current I, let's say this is the 10 amp, right? So this current 10 amp is going to happily flow from left to right, okay? So in such case, since there is no voltage difference, there's no potential difference, potential on these two dots, the same, okay? I claim that the resistance associated with this short is equal to 0. Now, if you look at this statement, right, so R is equal to 0. What is R? Resistance. 0 resistance. There's no resistance if there exists no voltage difference between these two dots. Okay, so like simply the current is just going to go right from left to right. Right. In this case, I specify the current flow in this way. Okay, so R is equal to 0. There is no resistance at all. Okay, mathematically, how do you appreciate this point? Well, since we know R is equal to V over I, right? This comes from Ohm's law. If there exists no voltage difference, then I know it's 0 divided by whatever. That whatever, right? In this context, as an example, I use 10. 0 divided by 10 is 10. What is R equal to 0? R equal to 0 corresponds to 0 resistance and is represented by a simple short circuit. When people say short circuit, they're always talking about some low impedance path, low resistance path, 0 ohm in this case, right? In the absolute case, right? In short circuits, R is equal to 0. 0 resistance. There's no resistance that will resist the current from flowing from left to right. 0. Okay. The only reason you can make this claim is because there is no voltage difference between these two terminals or these two dots. Okay. The dual of these short circuits is the so-called open circuits, right? So open circuit means you have to break this wire open somewhere, right? So over here, still two terminals, two dots, right? But in between, I have this open. Okay. So in this case, the opposite is going to happen, right? Over here, I have no voltage. But in this case, since I have an open, the current, even if I put in the current here, right, from left to right, even if I force some current, right, N flowing from left to right, but because there is an open, then this current is not going to be able to make from the left dot to the right dot. Just because I have an open. Open is just like a cliff, right? Open is like a cliff, right? You try to push some current there, but it's never going to make to the other end, right? Because you have a cliff. Right? It's going to send this current right down, right, into this open, without even making to the other side. In such case, the voltage difference between these two terminals, right? I'm using plus on the left and minus on the right, but it can be the other way around, right? There can still exist some voltage difference, the potential difference, okay? But since there is no current, so now mathematically R is equal to V over I, right? So what is V? V can be something, right? So in this case, let's say V is equal to 5 volts, right? So 5 volts. So what is I? I is equal to not 10. I is not 10, right? 10 is what I try to push, but it's never going to make to the other side. So therefore, I, in this case, is going to be 0. No current flow. No current is going to make from left to right because of this open. There's a cliff. So in this case, 5 divided by 0, I have infinity. Resistance associated with this is infinitely large. Infinitely large is completely opposite from 0. Infinitely large. Huge, huge, huge. Infinitely large resistance. It resists the current from flowing. Like qualitatively, that makes sense. Right? It resists the current from flowing because I have infinitely large resistance. Okay, so in such case, right? If I have R equal to infinity, then I know I have some open circuit. If R is equal to 0, I have short circuit. In short circuit, I have no voltage difference. In open circuit, I have no current flow. Okay, so let me just quickly summarize what we have learned. Okay, so we talk about Ohm's law. We talk about V. We talk about I. We also talk about power, right? So power is calculated as V times I or I times V, right? Poisson IV, if you will, right? That's kind of that's one mnemonic that I learned way back, okay? But of course, we know the underlying physics behind this V and I and P, right? So we know that P is equal to V times I or I times V. So since V from Ohm's law is equal to I times R, then we know this P is simply I squared times R. I squared times R, right? I times R. Alternatively, what you can also do, right, instead of using I times R to denote your B, right, you can use V over I to denote your I. So now you have V times V over R. So now you have V squared over R. So V squared over R or I squared times R, depending on what you're given, right? So if you have I and R, you can already calculate P. If you have V and R, you can also calculate P. Okay. All right. So this is just some sanity check that I put down over here. So again, R is equal to V over I. Okay. So if V is equal to 0, then R is equal to 0. And if R is equal to 0, you know you have some short circuit. If I is equal to 0, then you know R is equal to infinity, right? So plug in 0 on the bottom. So V over 0 is going to give you infinity for R, okay? And in such case, you have open circuits. Okay, so this slide basically summarizes what we discussed for the ideal voltage source, ideal current source, and ideal resistor. Okay, so this is pretty straightforward. I can plot IV curve here, right, or I and V. Okay, so in this case, for voltage source, right, so an ideal voltage source says that I can have whatever voltage that I specify to this voltage source. Okay, and this current, right, can be going in and out of this voltage source as long as this voltage, okay, is fixed, right? Even though I say it can go up and down, right, but you have to fix it, right? You have to fix it at some voltage, right? So Vs, for example, is 10 volts, right? Then the current associated with this voltage source going in and out can be either positive or negative, okay? Similarly, for the current source, you specify the current, right? So 10 amps. So after you specify this current, this voltage can go to the left or to the right, indicating negative or positive, right? It can be small or large, large negative and large positive, right? It doesn't matter, but as long as this current source or the current is maintained. That's what we expect from an ideal current source. For an ideal resistor, R here. So I apply voltage, I measure current, okay, and I take the ratio, right? So this R simply is equal to V over I, the ratio of voltage and current, right? So on this IV plot, right, I can just simply sketch out the slope. And this slope, notice that this slope, right, is a positive slope. And this slope is not simply just R, right? Because I'm doing I and V, right? So if you take delta Y over delta X, delta I over delta V is not R, it's 1 over R, right? So instead of using resistance, we have conductance, right? So that's why conductance can be sometimes very handy, right? In this kind of analysis, graphical analysis. Okay, saving the best for last. So I'm going to talk about, I'm going to slowly talk about KCL and KVL, right? But before that, I'd like to quickly introduce some technical terminologies for things that we will encounter later on. So AKA node, branch, and loop. Okay, so we're going to be relying on the definition or our understanding of node, branch, and loop, so that we can use KCL and KVL to analyze the circuit as the next step. Okay, so what is a node, right? So this is pretty intuitive, right? So a point where 2 or more circuit elements are connected, right? So in this case, I have a node, okay? So what is a branch? A branch is a path that connects 2 nodes, okay? So for example, right, so this can be one node, this can be one node, right? Or this is connected to something else, right? So I have a branch here, okay? And or in this case, I have 3 branches, 1, 2, and 3. Okay, single branch and 3 branches. And what is a loop? Okay, so a loop. So let me just sketch something else here. So let's say I have a loop like this, and this loop consists of 4 elements, whatever that element is. I'm using boxes to represent them. So this loop, okay, or a loop is formed by tracing a closed path, right? Keep in mind, it has to be a closed path in a circuit through some selected basic circuit elements. So for example, if I choose this one to begin with, right? So let's say I start from this point, okay, associated with this element, and then I go up, go to the right, go down, and go to the left, okay? This is a loop, and this is a closed path. This is a closed loop, okay? So I want to only pass each element once, okay? I don't want to pass this element more than once, okay? So I just want to start from here and end at the same point, okay? So this is my loop, okay? So we're gonna be using node, branch, and loop, okay, definition for us to understand our main topic here, which is Kirchhoff's laws. And as I alluded to you earlier, Kirchhoff's laws consist of 2 parts. First one is Kirchhoff's current law. Next one, the second one is Kirchhoff's voltage law, KCL and KVL. Okay, and these 2 laws are very important. Okay, they basically govern the general rules, okay, that you need to apply when you analyze a circuit. Okay, so it is important that you understand how these 2 rules are different and how they work. Okay, so let's look at the first one, Kirchhoff's current law, KCL. So by definition, KCL says that the algebraic sum of all the currents entering a node, okay, the algebraic sum of all the currents entering a node in a circuit has to be equal to 0. Okay. So what does that tell you? I'm going to go straight to the next slide first and come back. Okay. The algebraic sum of all the currents. So suppose I have a node here, and this node is shared by 3 branches, 1, 2, and 3. Each branch is going to carry some current. And this current can either flow into this node or out of this node. It doesn't always have to flow into the node, right? Who says it has to always do that, right? It can go anywhere, right? But the key here is the algebraic sum of all the currents entering into this node have to be equal to 0. This current I1 is entering the node. This here is my node, right? This current I2 is also entering this node, the same node. But this current I3 is leaving the node, right? They are flowing in different opposite directions. But if you look at the definition, what does it say? The algebraic sum of all the currents, how many currents do I have? I1, I2, and I3, right? In the example I show you, entering, right? The key here is entering a node, right? Any node, right? But I only have a node, right? Entering a node in a circuit has to be equal to 0. If I apply that definition, the sum of all the currents entering the node, the sum, I1, I2, and I3, has to be equal to 0. I know this has to be there right? The sum of all the currents entering the node has to be equal to 0. So what is entering the node? I1 is entering the node. I2 is entering the node. I add them up. But is I3 entering the node? No, right? I3 is leaving the node. So instead of making this I3 flowing into this node, what do I have to do? What do I need to do here? If I3 is going from here, right, from flowing out, right, let's say from left to right, in order to make it flow into the node, I need to attach a negative sign. That's all I have to do, right? Remember in the earlier part of this lecture, we say that you need to specify the direction of current flow. If the current is flowing from left to right, we can make it flow from right to left by attaching a negative sign, and that's exactly what I'm doing here. So I3 is flowing out. In order to make it flow in, I need to attach a negative sign. So over here, I can still do plus, right? Because I'm following the definition, algebraic sum of all the current entering the node. So I'm going to put minus over here. So now I1 is going in, I2 going in, I3 with a negative sign is also going in. The negative sign is critical. The algebraic sum of all these three currents has to be equal to 0. Now, by definition, we know this equation follows exactly that. Mathematically, this is what I'm going to do. So I don't want to see this negative sign. Okay. So if I don't want to see it, what do? I'm going to move it to the other side. So I'm going to have I1 plus I2, and this is equal to I3, right? Because I move it to the other side. Okay. So I1 plus I2 is equal to I3. If I do this, right, this is also valid, right? This is also correct mathematically. There's nothing wrong with this, right? So on the exam, on the homework, if you say something like this, it's perfectly okay, right? So, but how do we kind of interpret this equation, right? Since we kind of, deviate slightly from this algebraic sum idea, right, or definition. Okay, so notice that I1 plus I2 on one side, I3 on the other side. What is I1 plus I2? I1 plus I2 are the currents flowing into this node. Flow in, right? And I3 is the current that flows out. So alternatively, what I can also say equivalently is the current flowing into this node has to flow out. The current that flows into this node has to eventually flow out. Or in other words, I can also say the current that flows into, right, the sum of the currents that flow into this node has to be balanced, right? That's why I have this equal sign, has to be balanced by the current that flows out. Okay. In this equation, I can say the algebraic sum of all the currents, I1, I2, and negative I3, the algebraic sum of all these currents going into this node is equal to 0. But in the second equation, right, I changed the context a little bit, right? They're the same thing, but I changed the context a little bit by saying the current, the sum of the current entering this node has to be balanced by the current leaving the node, right? Because mathematically they are the same, right? All I did was I moved this I3 to the other side, negative I3 to the other side to make it positive. That's all. Okay, it's that simple, right? This is KCL, right? It's a law, right? It's some law that that we are trying to follow over here when we do circuit analysis. That's all. Okay, so again, if I use the second equation, right, all I'm saying here is the sum of the current entering the node has to be the sum of the current leaving the node. That's all I'm saying, right? One flows in, the other one flows out. Okay, so I3 in this case is leaving the node, while I1 and I2 are entering the node. Okay. What made this KCL possible, okay, is the so-called conservation of charge. Okay, in other words, whatever the charge that I have stored inside this node has to be equal to 0. If the net charge, right, stored in this node has to be equal to 0, then of course I know that what goes in has to come out. That makes sense. I1 and I2 goes in, and I3 has to come out. I1 plus I2 has to be balanced by I3. Okay, and this is all possible because of charge conservation. Okay, it's a very important concept, right? So something that you learn in your physics class, charge conservation, conservation of charge. Okay, so that's that for KCL, right? Pretty straightforward, I hope, right? All we are doing here is we follow the definition word by word, right? And we tackle it step by step. Okay, algebraic sum of all the current. Okay. The next one is KVL. So what does KVL say? KVL says the algebraic sum of all the voltages around any loop in the circuit has to be equal to 0. Algebraic sum, all the voltages around a loop, right? So let's first try to deal with one loop first. Voltages around a loop in a circuit has to be equal to 0, right? So again, there has to be some balancing action, right? In this KVL as well. Okay. So in this case, right? So let's see. So let me just go to this one over here. So the algebraic sum of all the voltages around a loop has to be equal to 0. Algebraic sum. So in this case, I have this simple circuit, and this circuit consists of 2 elements. So let's say I have R1 here and R2 there. Okay, and arbitrarily, I'm going to specify plus here and minus here across R1 and plus here, minus here for R2, right? And I'm going to call this one V1 and I'm going to call this one V2. So now I have this enclosed loop, right? I have a closed loop here. Okay, so that's where this loop concept comes in. So the algebraic sum. Now, if you look at this guy, right? So I'm going to start from here. I'm going to start from here first. This is my starting point. I go up to the right, go down to the left. I have to end up at the same point, right? So that's how I finish or how I complete my loop. So in the course of traveling around this loop, I encounter some voltage over here and over there as well. But notice that this voltage, right, goes from minus to plus. It goes from some small number to a bigger number. Okay, so that tells you that by going up, I'm experiencing, right? So let's say you're here, right, and then you walk around this loop, right? But you go up to the right, down to the left, right, back to the origin. So as soon as you are going up, you're experiencing this voltage rise. Voltage is rising because I have negative here on the bottom to positive. And keep in mind you're going upward, right? You're going up. So this is voltage rise. You follow this trace, this trail, to the right, there's nothing here because it's a short, right? The short means no voltage drop. That's good. When you're over here, you have to go down. You're going from some positive potential or some positive voltage down to some negative voltage. So in this case, what do you have? You have voltage drop, going from some higher potential to a lower potential difference, if you will, right? So in this case, right, so let me just write it down, rise, and this is voltage drop, right? Drop. Okay. And then you have to go back to the origin to complete this path. Okay. So throughout the course, I have voltage rise and I have this voltage drop. And the algebraic sum of this has to be equal to 0. In other words, the voltage rise within the loop has to be balanced by the voltage drop in the same loop, the same enclosed path. In other words, mathematically, I'm going to say V1, which is voltage rise, has to be balanced by the voltage drop, which is V2. Voltage rise, because going from negative to positive, I'm going from something small to something large, it's voltage rise. I go from something large to something small, I have voltage drop. Makes sense. Okay. So I have V1 is equal to V2, right? This is a balancing action that I alluded to you earlier. Okay. By using conservation of energy, right? What energy? Potential energy. Right? We're talking about potential difference, potential energy. The sum, okay, of voltage drops around the loop has to be balanced, has to be equal to voltage rises around the loop. In other words, if I follow the definition earlier, the algebraic sum of all the voltages around the loop has to be equal to 0, the algebraic sum. When I go from this point associated with the lower potential, the first sign that I see is negative. So I'm going to have minus V1 here instead of positive V1. I go up to the right, the sign that I see associated with R2 is positive. Okay, so I have plus V2. So the algebraic sum is going to be negative V1 plus V2. And V2 is positive, right? And this has to be equal to 0. And from this, you know V1 and V2, they have to be the same. Because voltage rise and voltage drop, they have to balance out due to conservation of charge, conservation of energy. Okay, so I'm going to give you this example here. Okay. So this example involves not just 2 elements, right, but multiple elements. And we are going to apply the definition, the algebraic sum of all the voltages around a loop has to be equal to 0, the algebraic sum. And I'm going to show you some simple rules for you to follow, right? And of course, once you know how to do this, you can develop your own rules, right? But those rules are basically self-contained, right? You know, once you know the principle, you know the concept, right? You can tweak it a little bit, right? As an example, I'm going to apply KVL in clockwise direction. If you know how to do this, right, you say, okay, I don't want to go clockwise. You can also go counterclockwise, no problem, right? But for me, I like to go clockwise. That's just how, you know, I do it, right? And that's how, you know, typically how your textbook do it as well. Okay, so that's kind of, you know, the convention that most people use. But again, there's nothing wrong going counterclockwise if you want. Okay, so I'm going to go clockwise, and the next step is pick an element to start, right? I have 7 elements here, right? And I need to pick a starting point, right? And the end point has to be the same as the starting point, right? So that I can have a complete loop, right? So usually I start from the bottom left, right? And if you want to tweak these steps a little bit, right, you can also start on bottom right or top left, doesn't matter, right? As long as you ended up in the same spot, completing the loop. Okay, so this is going to be my starting point and end point. Okay, so and I'm going to go clockwise, right? So going clockwise, I go up to the right, down to the left, right? Okay. So then now I'm going to apply KVL. I'm going to say algebraic sum of the voltage drops, okay, around the loop, okay, has to be equal to 0. But one thing that is very important to keep in mind is you need to watch for the sign. I remember sometimes there is negative, right? So if this is my starting point, I keep track on the sign. The first sign that I see associated with this element, right, I know I'm going to have some negative voltage, V1 minus V1. Okay. But keep in mind, it's algebraic sum, right? So algebraic sum tells me I need to plus. Plus what? Well, plus the voltage drop associated with the next element, right? But again, when I go up, I see negative again. I'm keeping track of the sign, right? So I'm going to have minus V2. Okay. Algebraic sum, so plus. The sign associated with the next element is positive, right? So I simply just do plus V3. Now I move on to this element, number 4. So the sign associated with this element is also positive. So I'm going to do plus V4. The sign associated with element number 5 is minus V5, right? So plus minus V5. Again, I always have plus over here because it's algebraic sum. The minus or plus depends on the sign that you see associated with each element, following this clockwise direction. So plus negative V5, and then what? Plus minus V6, okay. Minus sign again, associated with element number 6. And then the last element number 7, plus simply V7, right? Because the sign that I see is plus. We're not done yet, right? Because the definition says the algebraic sum of all these voltage drops around the loop has to be equal to 0. Right? So this is the equation, right? For you to apply, okay, for your KVL. Now, what you can also do, right? Again, if you have this negative sign that you don't want, right? What you can do is you move it to the other side, right? So this is what we just did, right? So I'm going to move this negative, 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 negative to the other side, right? So then I'm going to have V1 plus V2 plus V5 plus V6, and this is equal to V3 plus V4 plus V7, right? So that is to say, voltage rises has to be equal to voltage drop. How do I know this guy corresponds to voltage rise? Well, look at this guy, right? So this is my starting point. I'm going from something negative to something positive, right? So I know I have a voltage rise, right? Similarly, for element number 2, negative to positive, again, I have voltage rise, right? Keep track of the sign, right? But for number 3, I'm going from plus to minus. So this is voltage drop, right? Something higher to something lower, right? So the one that is rising will be put on one side, and those that are dropping will be put on the other side, right? So and you have to put equal sign in between, right? So that you know that voltage rises will be balanced by voltage drops. Okay. All right. So okay. I think I have one more example over here for KCL. Okay. So this is a rather interesting example. Okay. To show. So again, let's quickly remind ourselves what KCL tells us, or what KCL wants, right? So algebraic sum of all the current, okay, entering a node has to be sum to 0, okay? Algebraic sum of all the currents entering a node in the circuit has to be sum to 0. The concept associated with node, right? We're talking about node. In this particular example, it's very intuitive to say, right? So we know that these two elements are in series, right? Even if you don't know much about node or KCL or whatever, right? You can kind of tell that these two elements are in series. So now if I inject a current, right, I, okay, whatever this I is, let's say 10 amp, right? It's very intuitive to say that I1 and I2 are the same, right? If I1 is 10 amps, then I2 will be 10 amps because they are in series, and these two elements basically share the same current, which is 10 amps, right? But now, since we know a little bit about this KCL, right? So you can apply KCL to explain this this phenomenon, right? Instead of saying these two guys are in series and they share the same current, right? You can apply KCL over here at this node, right? So current I1 entering the node, current I2 leaving the node. Current I1 entering this node has to be current I2 leaving the node. Okay, so from that perspective, from using KCL, you can say that I1, and you can conclude I1 and I2 have to be the same, right? So all of the elements in a single branch carry the same current, right? You know these two elements are in series, but alternatively, you can also apply KCL to explain exactly the same phenomenon. Entering the node, leaving the node. Okay. So one generalization of KCL, okay, is something like this. So suppose if I have a big chunk of circuits, okay, sitting inside this circle, okay, whatever this guy is, okay, whatever the current going in, okay, has to come out, right? So if I have I1, I2 that go in, then I3 and I4, they have to come out, okay? So the sum of I1 plus I2 and the sum of I3 and I4 have to be the same. This is illustrated with this example here. So suppose inside this circle consists of 3 resistors in parallel. So when I inject some current I1 into this circle, okay, let's say 10 amp, the same 10 amp has to flow out, right, and appearing as I2, okay? But of course, right, internally, the current is going to be, the current that flows into R1, R2, and R3 will be different, right? But that's a different discussion, right? All I care about is the current that flows into this point has to come out, right? The current that flows into this big chunk of circuit has to come out, and those two currents, they have to be the same, okay? And later on, we're going to see that depending on the ratio of R1, R2, and R3, right, different current, okay, is going to flow through this R1, R2, and R3. Okay, so that'll be the discussion that you're going to see in the next part of the lecture. Okay. All right. So I wanted to come back and talk about this this reference node concept a little bit. Okay. So this is rather important because oftentimes when we specify voltage, okay, now we have to reference it to some. We have to reference it to something, okay, and that something, right, in the simplest context is usually your ground, right? Because ground carries 0 volts, and we like to use 0 volts, okay, as our reference, okay. And of course, you know, a reference is a reference. Even 0.1 volts can be considered as a reference. 1 volt can be considered as a reference, right? But one can be easier than just using 0 volts as your reference. Okay, so this is one important concept that I wanted to bring up. Okay, so suppose I have this voltage, okay, Vs, right? So this Vs, okay, is the voltage drop between this node and this node, right? Again, so this Vs is your potential difference, right? So remember the VAB example that we discussed earlier, right? So this voltage drop, right, is this voltage minus this voltage, right? But what is this voltage, right? So this voltage has to come from some reference, and that reference, right, I'm going to use ground, okay, to represent my reference node. Okay, so again, right, the voltage across a circuit element is defined as the difference, potential difference between node voltages. Okay, so again, over here, I have VA, right? So if I ask you, right, what is VA, right? Depending on if if I ask you to calculate the voltage from here to there, right, or from minus to plus, right? If it's from plus to minus, you will take this voltage on the right minus this voltage on the left. Right? If I ask you to find what is this voltage from left to right, then you will take the whatever the voltage associated with the negative terminal minus whatever associated with the positive terminal. And similarly for VB, I'm going to take this voltage, this node voltage, minus this reference node. Okay. So now you see that if VB, right? So if I were to give this guy with some numerical number, if this guy here is sitting at 1 volt, right? This node voltage is 1 volt, then VB is going to be 1 volt minus 0 volts, which is 1 volt. 0 volt because I have my ground, 1 volt because as an example, I say, this is my 1 volt, right? Now, if I change this reference to something else, if I say this reference node is not sitting at ground anymore, but this is sitting at another voltage, which is 0.1 volts, then now this VB is not going to be 1 volt anymore. Instead, it's going to be how much? If this guy here is no longer sitting at 0 volt, then VB, I'm going to write it here, VB is going to be 1 volt. Same over here, right? This is always kept at 1 volt as an example, minus 0.1 volts, which is going to give you 0.9 volts. Okay, so you have to be very careful here, depending on what you set for your reference, right? This VB can be different. Okay, so this VB, right, again, is a potential difference. You take this voltage minus this voltage, and if this voltage is not set to a ground, right, and you have some offset, then this VB is going to be different. Okay. So so that's that for this part of the lecture. Okay. So I'm going to stop recording here, and I will be moving on to the next part of the lecture shortly.